This learning video covers what causes earthquakes and where are they most common. It also covers the elastic rebound theory, a very important concept on how the Earth deforms. Here are the learning outcomes for Unit 10b. This particular video is going to cover number 10, so go ahead and pause and write this at the top of your notes. Here's an outline of what we're going to cover. So we'll start with the simple question, what is an earthquake? And basically, an earthquake is shaking of the Earth's surface or interior. This is called a seismic event by people who study earthquakes. Seismo is a word that means shaking. So a seismologist is someone who studies earthquake waves. A seismometer is the instrument that records earthquake waves. The seismogram is the paper that has those little squiggles on it. Shaking of the Earth's surface can occur from several different kinds of things. You could imagine a meteor that might hit Earth. That's going to cause shaking. You could have magma moving through a volcano, and that causes shaking that gets registered on seismometers. Underground nuclear testing is also something that shakes the Earth, and that can be registered on the instruments. As well as in some cases where water waves are extremely big and pounding the shore, breaking waves can also be recorded. But for our purposes, we're going to talk about the main reason that earthquakes occur, and that is because there is sudden movement along a fault. So here's a little picture showing a fault, and hopefully you can tell what kind of fault this is now that we've had some practice. Maybe pause the video and see if you can come up with what type of fault this is. So if you said normal dip-slip fault, you were correct. This is a dip-slip fault because it's dipping, and it's normal because the hanging wall on the right is going down relative to the footwall, which in this case is on the left. And we can tell that by looking at the offset rock layers. So when we have a fault, either side of the fault are rocks that are kind of under pressure, and they're stuck at this fault, right? They're not moving. And as the stress continues on either side, let's say this one is trying to go up and this one is trying to go down. So right there, pushing, pushing, pushing. And then finally, that stress overcomes the strength of the fault and it moves suddenly like that. That is an earthquake. So it's an energy released by a sudden slip along a fault. We're going to stick with faults. And that energy is sent out in all directions from where that very first break starts. This follows the buildup of elastic strain, which we'll get to in just a minute. So here's a similar cartoon to the one I was just showing you. Again, this coincidentally has a normal dip-slip fault with the hanging wall on the right, but that's not always the case. And there's a couple of things I want to alert your attention to. The earthquake does not start at the surface of the Earth, even though that's what we tend to concern ourselves with. The earthquake occurs somewhere at depth along that fault. And what's shown here with the red dot is the focus, which is the point where the earthquake first begins. It's the first place on the fault that starts to experience slip. And it sends energy out in all directions, as it's shown by these sort of pulses of shaking going outward. Above the focus, directly above on the surface of the Earth, is the epicenter. And many of us are familiar with epicenter. When there's a large earthquake, you hear about where the epicenter was. And that's because we live on the surface of the Earth. And that is the place on the surface closest to the focus. So that is going to be the place that experiences the greatest amount of shaking. If you live over here, you're going to maybe feel these waves from the earthquake, but they're not going to be nearly as strong as if you were very close. A few other terms here. If the fault breaks the Earth's surface, they don't always, sometimes they remain below the surface. But if it breaks the surface and you could go out and map it, you would have what's called a fault trace. That's the surface expression of where that break meets the surface. And then this is a fault scarp, which is actually the fault surface that's been exposed because the hanging wall has gone down. And this little cartoon is showing some lines indicating the direction that this block has moved. It didn't move sideways, it moved down. And those are called slicken lines. And those can tell us what direction the two sides were moving relative to each other. Here's an actual picture of a fault scarp. This one's in Mongolia. There's a person here for scale, and you can see these slicken lines pretty well that are telling us how things moved on either side of the fault. Okay, so let's talk about the elastic rebound theory. So this is the idea that the ground behaves elastically when strain is building up before an earthquake. So remember we talked about the three kinds of strain: elastic, plastic, and brittle. So the earthquake itself, when it happens, is brittle. It's a break in the rock. But before it happens, the strain that builds up is elastic. We first have a force applied, maybe plate motion is moving two plates in opposite directions. Here is an example over here, a little cartoon of some land that's not deformed yet. There is a vertical fault here. That would be a strike slip fault. And then there's a fence built across because that's going to illustrate the elastic strain. As the two sides move, as shown by the arrows, in between them, remember that fault is stuck, so the rocks aren't breaking yet, but they start to deform, they start to bend. And that is the elastic nature of the bending. And we can see that in the fence here, which now has a curve across the fault. The fence hasn't broken yet, but it is curved. Looking at this analogy over here with a stick, you could take a stick and you could bend it as the person's doing here, and now that stick is kind of curved. And eventually we're going to overcome the strength of that fault and we're going to break it. And so the rocks break, that's when you have your earthquake. And what you'll notice is the fence has returned to its linear position or linear shape. It's offset now, but it's now linear. It's no longer curved, right? And that's the elastic part. It went back to its original orientation. Same with the stick. The stick is bent, but once it breaks, both pieces are now once again straight. So we have elastic strain building up. Once the earthquake occurs, the elastic strain is released and we do end up with brittle strain. The last thing we're going to talk about is, where do most earthquakes occur? Hopefully by now in this class you recognize this image of plate tectonic boundaries. Where plate tectonic boundaries occur, we have two giant plates either sliding past each other, pulling apart from each other, or pushing towards each other. Maybe one of them is subducting. These are all places where we have stress. And that's where faults occur. So active plate boundaries are where we have most of our earthquakes. So this is showing the Earth without the plate boundaries. Each of these dots represents an earthquake. The red dots are earthquakes that are shallow, close to the surface. The yellow ones are of intermediate depth. And the blue ones are the deepest one, hundreds of miles perhaps. And they are not just randomly distributed around the globe, they are concentrated in certain areas. So let's take this map and move it a little bit in position. And now what I'm going to do is I'm going to toggle between this map and the plate boundary map. Okay, I'm going to go back and forth. Now your eye could maybe pick out this diamond-shaped plate, which is the Philippines plate. You've also got all of these subduction zones that go around the Pacific, including down here. So let's take a look at those. See how those earthquakes all fall along the plate boundaries? Now over here we have the Mid-Atlantic Ridge, and notice what color the earthquakes are along the ridges. They're red. So divergent plate boundaries tend to have shallow earthquakes, and we'll look at that in side view in just a moment. So let's look at the Mid-Atlantic Ridge and the East Pacific Rise here, back and forth. Not a perfect match, but you get the idea. That's where most earthquakes are. Now, not all of them, right? There are certainly exceptions. There's some earthquakes here in the middle of the United States, and there's some earthquakes out here in Hawaii. Remember how I mentioned that magma moving under a volcano can cause shaking, cause an earthquake. So this is an image I just printed out a few days ago. This is from the USGS, which is the U.S. Geological Survey site on earthquakes. And hopefully you see the plate boundaries again. If I jump back, I've still got my Philippine plate over here, right here. These are earthquakes that occurred in the past week when I downloaded this image. And as you can see, with a few exceptions, they are all along the plate boundaries. Now here's Hawaii again. Hawaii has a lot of small earthquakes because there's a lot of magma moving, especially recently. Here's a couple earthquakes in Texas, not sure what's going on there. In this class, we don't really have time to talk about what's called intraplate earthquakes, earthquakes that are not along plate boundaries, but within a plate. So we're just going to focus on these other ones. The size of these circles indicate the magnitude of the earthquake. And so in this website, which I really encourage you to check out, you can click on any of these and get more information. So for example, I clicked on this biggest one right down here, and it lights up in blue, and I get this information over here, and then you can click on it again and get even more information about it. So this one was a magnitude 7.3. It occurred on March 30th, 2026. This is the latitude and longitude. It was 121 kilometers in depth, and you can get a lot more information like that. So let's look at these earthquakes in terms of how deep they are. This is a divergent plate boundary, a mid-ocean ridge. Remember that earthquakes only occur in lithosphere, and in divergent plate boundaries, the asthenosphere is very close to the surface, and the lithosphere is pretty thin, right? We're creating new crust as it moves apart. So here we have primarily shallow earthquakes, because you can't have earthquakes that are not in the lithosphere. We have our divergent zone here, so we're going to have normal faults there, and same with this over here, right? We have tensional stress going on in these areas. And then where we have this transform fault, we have shear stress. And remember, these inactive areas out here are sometimes called fracture zones. Here are some transform zones that go through continental crust instead of ocean crust. This is the North Anatolian Fault in Turkey, and this is the San Andreas. And California has been turned sideways so that the two faults sort of look similar to each other in terms of their orientation. They're both right lateral strike slip faults, and they both have similar slip rates. So these also have shallow seismicity. And of course, we live near the surface, so these are very dangerous earthquakes. Even if they're only a magnitude 5 or 5.5, they can be very devastating because they are so close to populated areas. Finally, we have the convergent plate boundaries. And this is where two plates come together. So this is a side view, and the lithosphere is shown in this kind of purplish color, and the asthenosphere is in the orange. And remember, the asthenosphere is weak. It cannot have earthquakes. So we have earthquakes near the surface where the two plates are coming together. But then we also have earthquakes in that downgoing plate, right? And that's where we get our earthquakes down to maybe 700 kilometers. We can have earthquakes very deep. And this region here was identified by seismologists before we really understood what it meant, and it was called the Wadati-Benioff zone. So it was a zone of earthquakes that they saw in convergent zones and eventually realized, oh, that's the lithospheric plate going down into the mantle. You also saw this in our plate tectonic lab recently. This is underneath the Tonga Trench, and these earthquakes are colored by depth, and the idea is that this represents the Pacific plate going underneath the Tonga Islands. Finally, if we looked at one of these on the side view and projected it up to a map, we could actually tell which plate is going down, because the shallow earthquakes will be where the plates meet, and then the deeper and deeper earthquakes that are projected to the surface are going to be in the downgoing plate. So in this case, in the Japan Trench, we have the Pacific plate going under Eurasia. If we come back to this diagram, you can see there are deep earthquakes, such as here. We have those yellow and blue earthquakes, those deep ones that tell us where the trench is. So here we have the Pacific plate going under the Indian Australian plate, and we know that because of the change in depth of the earthquakes. Summarizing what we've done so far, an earthquake is the energy released by sudden slip along a fault. The elastic rebound theory indicates that rocks deform or strain elastically in response to stresses. Most earthquakes occur along active plate boundaries. And finally, the deepest earthquakes tend to be associated with subduction zones.